Okay, so ideal gas law. What you should have read about last week when we did a reading guide on the kinetic molecular theory is it shouldn't matter what the gas is. If gases are not slow, so low temperature, or close to each other, high pressure, they all behave basically the same. That's what, and I don't think you have to write down what Avogadro's law is, so I don't think this is necessary for you to write down. But that's what Avogadro's law states. So more than just mole conversions, Avogadro dealt with gases. What he said was that equal volumes of gases at the same temperature and pressure contain the same number of molecules. So again, what does this mean is that no matter what size of gas it is, a large gas, a small gas, we can use the ideal gas law for any of these. And it also lets us know that for any gas at standard temperature and pressure, 1 mole of that gas would occupy 22.4 liters. I actually have a box with that over here on the side of the room to remind you about what size that is. So because gases are so tiny compared to the space that they occupy, we're able to say this. And I like to use the analogy of it doesn't matter if I had 24 Josies in this room or 25, think of it, I don't know, who's a really big offensive lineman on the football team, but you get the point. This room can fit 24 individuals, regardless of the size. So that's what Avogadro's law is basically stating as well, is that the gases themselves, yeah, they can vary in size. However, since the space that they move around in is so much bigger compared to them individually, it doesn't matter what the gas is. Okay, so that's the kind of rationale behind it. Again, you're not assessed on that. The 22.4 liter number is kind of nice to just have in the back of your head when you're talking about 1 mole of a gas at standard temperature and pressure. The ideal gas law itself is PV equals nRT. This equation is given to you, so unlike what I went over last class, which AP must deem background knowledge, this one you don't have to memorize it all because it's given to you. However, this gas law is very unit specific. Pressure has to be in atmospheres in order for this to work, which means we might have to convert from milliliters of mercury or torr into atmospheres. Volume has to be in liters, and that's not something that we required last class either. Lowercase n means the number of moles. Again, lowercase n is the abbreviation for number of moles. You'll see that again when we talk about partial pressure a little bit later in class as well. Temperature has to be in Kelvin. Now that's consistent with what we went over last class. This class with Charles' law and the combined gas law, since temperature is in the denominator of those equations. Temperature is the measure of the average kinetic energy. That's why the Kelvin scale is the best for that. Now the reason why all of these units have to be, or all these variables have to be unit specific, is because of R. R is the ideal gas law constant. Again, just like 3.14 is a constant that makes circle math work, R value makes this work. Now, I've already given you one R value in notes a little while ago, 8.314 joules per mole Kelvin. This is the R value that you're going to use. So I don't know why they give you multiple R values on the equation sheet. However, this one with the unit of liter atmosphere per mole Kelvin is the one that you would be using whenever you use the ideal gas law. I don't believe that you would be using the root mean square equation at all on the AP exam anymore, yet they give you that constant. So a simple problem would not have you have to deal much with conversions because maybe they'll give you the pressure in atmospheres, volume in liters, so on and so forth. But this could be a, boy, I have to do 4 conversions before I even solve the dang problem type problem. Now, I don't know if we actually have to write down this, but just a reminder then of how does this type of problem vary from what we went over last class. Because as we get further in AP chemistry, it's no longer the individual skills that students struggle with. It's knowing what to choose and when. The difference between what we are covering right now and what we covered all of last class period is moles is now involved. And remember, if moles is involved, grams could be involved. Because heck, you could convert from grams to moles if I gave you what the gas was. So that's the big difference. Last class was a before and after. Here's the volume temperature before. Now what's the new volume at this temperature? Or pressure, volume, temperature, combined gas law before. What's the new this afterwards? Ideal gas law is not a before and after. It is much more of a tell me this under this set of conditions. And the biggest difference is it involves either moles, like this one does, or grams we could give you as well. Again, remember, a couple ways you could solve it. You could either plug in immediately, or you could isolate the variables, what the math department always has suggested when doing any sort of calculation. Again, I'm not going to go through the math of this because it is fairly straightforward algebra. Of course, if I gave you 1 mole and the writing of 1, I probably should do a better job with significant digits. However, that is about 6-minute talk on the ideal gas law because it is fairly straightforward. It's just a matter of you getting used to using it. So that's where I'm going to end notes for this first part of class. What you guys have then are 2 things. One is a sheet with practice problems that are just on the ideal gas law. Don't do the one that says partial pressure in it. So I believe this is the ideal gas law homework sheet. Once we get done with that, we are going to transition into the molar volume reading guide, which is going to kind of combine this idea of ideal gases, but take it a step further.
Scuba diving.
In the spring. All right, so showed you a statement to start off the ideal gas law, dealing with Avogadro, which we remember from mole conversions. John Dalton, we might also remember from atomic theory back in Chem 1. He also worked a lot with gas laws. And again, this first statement here isn't necessarily anything that you're going to be assigned to regurgitate back out. It's more of the statement that allows us to do the math that we're about to do. So again, Avogadro said, hey, each gas is basically the same because of the space they occupy versus the space that they are. John Dalton said if you have a mixture of gases, like the air that we breathe in right now is a mixture of gases. As long as they are under ideal conditions, which remember, gases behave ideally when they collide perfectly elastic with one another. One does not affect the other in any way, shape, or form. So even if 2 things were polar, they don't attract or repel each other. That is to happen when the temperature is high enough and the pressure is low enough. Because when temperature is low, things move slow, they're more likely to interact with one another. When pressure is high, things are close together, they're more likely to interact with one another. So Dalton's law says, if gases behave ideally, they act independent of one another. So, one of the equations that you'll be given on your equation sheet is the total pressure in a container is equal to the individual pressure of each gas. P1 plus P2 plus P3, so on and so forth. When I look at the equation sheet, they actually call it PA, PB, and PC. So pressure of gas A, pressure of gas B, pressure of gas C. But again, each gas will contribute to that total. So recall the other day when we were doing the can crushing and I looked up the pressure in the air so we could figure out the pressure of the can afterwards. Nitrogen's the main gas in our air. It's roughly 80%. Oxygen is a shade under 20%. So mainly it's those 2 gases in our air that contribute towards the total pressure. Now that's as simple of a way that we can break this down. There is another way that we can address partial pressure, and that is taking into account kind of the ratio of each gas. Like for example, when I say there's 80% nitrogen, 20% oxygen in our air, well then we could figure out what's the pressure due to oxygen, what's the pressure due to nitrogen. So the equation that will be given to you is 2 parts. First, this capital X stands for mole fraction. So maybe you don't need to write down in words underneath mole fraction, but the equation, X1, and again our equation sheet calls it XA for gas A. Mole fraction is the moles of whatever gas you're looking at, so I'm saying this is N1, divided by the total number of moles. Again, our equation sheet uses A's instead of 1's. If you know the mole fraction, then you can plug it into this equation at the very bottom of this page. That is also on your equation sheet. The pressure of gas 1 equals the mole fraction of it times the total pressure. So if we simplify it, if 80% of our gas in this room is nitrogen, 20% is oxygen, then, you know, roughly at that point we have 80 divided by 100, so 0.8 would be the mole fraction nitrogen in this room. We multiply that by the pressure in this room, it would tell us the pressure of just the nitrogen. So each gas acts independently of one another, but we can solve for the pressure of each individual gas. Now, what I'm showing you right now in this slide is how you're typically assessed partial pressure when dealing with a paper problem. So, textbook, question on a web assignment, question on a test, something that's directly in front of you. So this is important to note just for, this is kind of the, what you'd see probably more likely on a test. Because heck, you could be asked to solve for the number of moles of something, and then part B is now use that to solve for the pressure of that gas. Think about these part A, part B type questions. My last two slides for this set of notes here is going to go over what can we do in the laboratory. Because we cannot measure the moles of each type of gas when we're working with gases in the lab. That's the tricky part of this. So we have to figure out a different way in order to figure all this out. So this is almost like a two-part notes where here's the textbook style question. Now I got to prepare you for the lab style question. So we're going to be using a new piece of equipment called an UDIometer, which I abbreviated UDI on the board. UDIometer is a glass tube that we can collect gas in. And what we have to realize, and I'll draw this out on the board in a minute here, is that the pressure inside when we collect the gas is going to balance with the pressure on the outside. So this is almost like an old-fashioned barometer when I talked about how pressure was measured way back when. Let me get through the pressures inside the UDIometer, then I'm going to draw it out for you. Maybe that'll help out. So, we are going to collect a gas in the lab. That gas will fill in part of this tube. So that would be one of the pressures for that three pressures in here. Remember that a unit of pressure is a millimeter of mercury? Well, we are not going to be collecting gases in a mercury bath because we can't use free-flowing mercury. So instead we use water. But here's the problem with water. Water itself can give off water vapor. Remember vapor pressure? Any given temperature you can have some pressure of a gas. Water and its vapor pressure is based upon temperature. You picked up on the way in a sheet that gives you at any given temperature of 0 through 50 degrees basically Celsius, what is the vapor pressure due to water. So this little sheet here will be handy when it comes for the lab that we're going to be doing on Friday. We're going to be practicing this probably next class. I don't know if we have time today to get out the UDIometers and practice it. Maybe we do. But again, this is something that we'll need to keep handy with us. And lastly, remember that pressure is measured in millimeters of mercury. Millimeter is a distance. It's a column height. We will be using a meter stick and measuring our column height. However, again, kind of a weird thing, is that water, I don't know who figured out how to convert from millimeters of water to millimeters of mercury. But if we have to eventually report our answer in millimeters of mercury, we take our millimeters of water and we divide it by 13.6. That's the last thing I say in this slide. So I'll let you jot this down, and I'm going to switch over to Smart Notebook, and I'm going to draw out kind of what it looks like. And based upon how much time we have today for practicing after I get through notes, we might even have you just try to set up the apparatus today. I got Alka-Seltzer, and we can collect gas with that. Top plop fizz fizz. So, similar to when we did the can crushing, you're going to have a tub of water in it. Except for this time, you're also going to have the oodiometer in it. So again, this right here is the oodiometer. So we got water in it. So let's say that we collected gas in our oodiometer. So again, it's open at the bottom, closed at the top, so we can collect the gas inside of it. Actually, there's volume measurements. We'll talk more probably in the next class about what those volume measurements mean. Inside of here is what we could call P1 or PA, whatever. That'd be the gas that we're trying to collect. So depending upon the chemical reaction or whatever we're doing, there's going to be a gas inside of there. Because remember, what that gas is doing is it is pushing down on that column line. I mean, gases are bouncing all around, including bouncing around there. Not only that, but inside there's also water vapor, P of H2O. And the reason why old oodiometers were with mercury is mercury didn't give off vapor like water did. So you're able to avoid the math that we have to do. Unfortunately, water does give off water vapor. And then lastly, you have what I would call pressure of the column, P of column. So we will physically get a meter stick out and measure from the top of the water in the tub to the water in the oodiometer. Because if that column is shorter, that must mean there's a greater pressure pushing down. All three of these pressures balance out at that line right there with the pressure due to the room, which I would call atmospheric pressure, P of ATM. Because room pressure is pushing on the surface of that water in the tub. The only place the water can go is up the tube. So at some point there has to be a balance between the two. That balance we can represent mathematically. Where room pressure would equal the pressure of the gas, pressure due to water vapor, and our column height, which remember our column height is in millimeters of water. If I wanted to convert that to millimeters of mercury, I divide that by 13.6. I would not anticipate that this type of math you would see on a test. However, for us to do partial pressure in the laboratory, this is what we have to do. The total pressure equals the pressure of the parts. What I'm going to do to wrap up here is I'm going to go back to PowerPoint and show you a sample problem that you don't have to write down, because we're going to give you a chance to practice a little bit here in a minute. But we kind of have to have our brain set in two ways here. One is the partial pressure that's more textbook oriented, that's mole fraction, and one that's more laboratory based, which is this right here. So again, hopefully now that this slide, after you see my drawing, makes a little bit more sense. So, typical problem would give you the room pressure right away, so at 780 millimeters of mercury. It needs to give you the temperature because the temperature with this sheet will allow you to solve for the P of H2O, the water vapor pressure. The volume of the gas is something that we're going to address more next class period, but there are markings on an odometer just like there is on a burette. Kind of starts upside down, where you can measure the volume of a gas collected, because we're going to have to do a step with that and actually combine that with the stuff that we just did on the reading guide. It'll give you the column height typically, so it's 25 millimeters above the outside water level. So then what you would have to do is realize, like I showed before, room pressure would equal the pressure of all the different gases in the tube. Then you just plug it and solve. So this is kind of an application of P total equals P1 plus P2 plus P3. So Dalton's partial pressure law states that these gases act independently of one another, but they should balance out to the total pressure, which would be the pressure in the room. And if I were to solve this one, it would be 758 millimeters of mercury. What I can tell you is partial pressure is a very common thing for students to be assessed on. Now, what I'd like to do is first give you a little practice in the math. The other sheet you picked up on the way in that said ideal gas law and partial pressure, I would skip the first three problems if I were you. Those are all ideal gas law problems, so we can do that some other time. Then, questions 4, 5, and 6 are more textbook style partial pressure problems. Then 7 on through is when we focus a little bit more on laboratory style problems. Based upon how much time that takes, we may or may not even practice using the odometer to wrap up the class period today. If we don't get today, what we're doing right away to start next class is I want to get us used to doing laboratory work with this piece of equipment prior to us doing the lab on Friday. Okay?